Very good. Example. Let us talk about the equivalence classes of identity relation. Identity relation. Well, suppose you have a set, let A be any set. We define the identity relation as follows. We say that X is related to Y if and only if X is equal to Y. So equality is just the identity relation. Is this relation an equivalence relation? You can easily check that. This relation is an equivalence relation. It is reflexive, symmetric, and transitive. Very good. So now, given any element like A in relation in set A, you know that we have a relation, the identity relation. And this is an equivalence relation. So we can define the equivalence class of A. The equivalence class of A is all elements in set A such that X is related to A. Okay. So what's the meaning of that? It means that we are looking at all elements in set A that X is the same as A. This is how we define this relation. This relation is equality, the identity relation. So we're looking for all elements in set A that are the same as A. The set of all members in A that are exactly A. Well, the answer is obvious. There is one element in set A that is exactly the same as A. So it's going to be set including A. Equivalence class of A is equal to a set with only one member in it. So the equivalence classes of elements of set A are sets with only one member. So if there is no repetition in set A with distinct elements, of A, then if you want to form a partition for set A, it's going to be as follows. For example, you have equivalence of class of A, equivalence class of B, equivalence class of C, equivalence class of D, and you can continue this process. All of these have only one members in them. Equivalence class of A is set including A, equivalence class of B is set including B, and so on. That's how we form the equivalence class when you have the identity relation. Guys, again, for each relation, you have different analysis. This is for identity relation. Just a quick note. Note that suppose A is a set and R is an equivalence relation on set A. Let A and B are members of set A if A is in relation with B, then for sure you can conclude that the equivalence class of A is the same as the equivalence class of B. If two members are related together, then their equivalence classes are the same as well. Why is that? We define the equivalence classes this way. This is the set of all X values in set A such that X is related to A. And this guy is the set of all X values in A that X is related to B. A is in relation with B. If you take any element in this set, that element lands in the second set. The first set is a subset of the second set, and the second set is a subset of the first set. If I take any member in this set for any X in equivalence class of A, I conclude that X is related to A, am I right? At the same time, A is related to B. So X is related to B. So X belongs to equivalence class of B. So equivalence class of A is a subset of equivalence class of B. Equivalence class of A is a subset of equivalence class of B. The same argument here. If you take any member in this set, that member lands in the second set. For any X in equivalence class of B, by definition, X is related to B. But you have an equivalence relation, am I right? This relation is an equivalence relation. X is related to B. B is related to A. So X is related to A. So X belongs to equivalence class of A. This guy gives us the relation that B, the equivalence class of B, is a subset of equivalence class of A. These two are subsets of each other. By the definition of being a subset, they must be equal. 1, 2, 1 is 2. They are the same thing.